Hello, good evening. Let me just share my notes. Okay. This is week 4 of Essential of Data Science with our software, Sampling Theory and Linear Regression Analysis. I am Kamna Mishra from School of Mathematical and Statistical Sciences, IIT Mandi, and the course instructor is Professor Salab, who is from Department of Mathematics and Statistics, IIT Kanpur. Uh, these are the class timings for the class and etc. Other important links. Okay, so we will go straight to the main points. If you have any question, you can ask now or later. Okay, so basically, in this class, we will go through the sampling package. If you remember, then in the last class, we have gone through the sample. Okay.
ए सरिता प्लीज यार मत तुम नॉट से तुम लेके पहुंच जाती हो यार वहां पे मत इन सब लोगों की बात करो
Excuse me, sir. You can mute yourself. Thank you. Okay. Uh, we will see now this like in I as I have said that in the last class we have gone through this package sample. This time we will see so in the sample package what do we have? So we can do like here it is open already. So in the sample package we can just see that if replace is false, that means replacement is not allowed. That means it is SRSWOR. So without replacement, simple random sampling. And the sample dot int is basically in place of giving x as a vector, we can just give n as 100 to 100, and it will take basically a vector from 1 to 100 or 1 to 200 on its own. So we do not need to define x. uh, Another thing is that when we change the replace, this replace,
मैम
yes,
can you please repeat this the earlier session. How
yeah,
much
sure.
time has elapsed, ma'am? Is it only 2 or 3 minutes?
uh, uh, can you repeat what did you say?
Ma'am, I just wanted this. I have joined just now.
Yeah,
You,
okay, sure, I can repeat it, no problem.
right, ma'am. Thank you very much, ma'am.
Okay. uh, so basically let me see that we can open this. uh, Okay, so here are some examples which we have used in the last class. So basically, we have two packages here, as you can see, sample and sample.int. So in sample, you can see that in x, we need to give some array, some vector. So in place of x, if we will give some vector, so let's say I am just writing sample 1 to 10. If I will run it, so to run, either you can use run or you can use just control enter. So here it has given me any sample in between 1 to 10. uh, so so because I have not defined here the size etc, so it will just write 1 to 10 in any form. And also you can see that default value is false. So default value is false, that means it is a simple random sampling without replacement. So if I will give, let's say, 5, and I will not give anything, uh, then it will be basically 83125. However, if I will change the size to, let's say, 5 here also, and if I will do replace equal to true, so replace equal to true means if it has a sample,
with
If it has
replacement.
what?
Okay, right.
Okay. Okay. So simple random sampling. Okay, let me just write it here. So it is basically SRS in two parts. SRSWOR, SRSWR. So in SRSWOR is basically without replacement, and this is with replacements. So if I have a population size of 10 and 10, then if I have taken 5 from here, it cannot take 5 again. So not again. But in this, it has no rule. If I have taken 5 or 10 or any number one time, it can take it again. So we will see here. So if I'm saying that 1 to 10 size 5 replace true. So here you can see that uh, here you can see that in sample 1 to 10 it has replaced 7, 6, and then 3 and 3 is repeated again. So this is basically between the uh, with and without replacement. The another thing is that prob is equal to null. So prob is equal to null means probability we are not giving. Uh, okay, so let's say I have 1 2 3 4 up to 10. So the probability of coming 1 is basically 1 by 10. This is 1 by 10. This is 1 by 10. And this is 1 by 10. If it is totally random. But if I say that there is some value which has higher probability to come, and then also I want you to take it random. So I'm saying that it has probability 1 by 10, but for this it has probability 1 by 5. So here I have given that for the first one the probability is zero point 0.1, for the second one, but for the third one I'm saying that probability is zero point 0.2. Okay, so if I will run this, so here you can say that 8 is coming two times, because for eighth value the probability is high, and the 3 is coming one time. If I will run it again, you can see that 8 has repeated again more, and then 1 is repeated. So it is not a necessity that 8 and 3 will repeat more, but there is high chance that it will also repeat. So you can see that 3, 8, 8, 8. So most of the time 8 is repeated. If I will run it, let's say 100 times, then there is high chance that most of the time that 3 and 8 is coming. So you can see here 3 and 8 is coming, 3 and 8 is coming, 3 and 8, so etc etc. So if I will run a command large enough number of times, then we can see that basically the probability that 3 and 8 is coming is very high. And 1 2 3 4, so 4 is coming is basically low, like according to what we have given. Okay, so this is basically the use of sample and sample in sample.int. It is just one difference is that in place of x, we need to give n. So n
Ma'am,
is, yes.
excuse me, ma'am. I mean, this class is basically the third week chapter we are covering, I think so.
Right now we are covering the fourth one, but this one is the third one I'm repeating.
Yes, yes. Because, ma'am, what I thought that he was calling. Okay, thank you very much, ma'am.
Okay.
Please
Uh,
continue.
okay. So in sample.int, all we need to do is that we need to do n, and in place of like 1 to 10, we need to give just 500 and then size 20. So it will take any 20 numbers in between 1 to 500. Okay. The another way is that we can choose that, like if I will run this x is 1 to 500 and sample is from x such that x is divisible by 15. So it will take only the samples which are divisible by 15. So we can give a particular command, but means particular condition, that we have a population, but we need to take sample from a certain population. Just a minute, I need to take this call. हेलो सर, मैं क्लास ले रही हूँ एक्चुअली। मैं ठीक है सर, मैं करती हूँ। ओके। Okay. Another thing is that we do not need to take the sample only from the numerics. So only from the numerics means we can take the samples basically from letters also. So if I will say Z1 this, and if I will take sample, then I can take the sample from HDI. So basically, it will give us that we can take the sample from whatever. Uh, Population we have, whether it is a character string or a numeric string. Okay, so this was basically regarding the last class, that how do we take the sample, etc. Okay, so move to the today's class. We need to take this sampling package. So the now this sample and sample.int, as you can see here, sample in bracket base. So it comes in the base package, so we do not need to require any package to install. But if I will take this library, and if I will do sampling, then it is saying that there is no package called sampling. So for the sampling we need to require the package. Okay, so now if I will run,
I mean, ma'am, the library package is not available in the sampling package initially or the base package.
yeah, so sample is available in the base package, but the sampling to use the library sampling is not in the base package. Or we say that the function which we want to use, that srsw OR. So right now you can see SRSWOR and WR, but if you will start it again, then it will not show because it is not in the base package. So you can see that SRSWR, for that we need to require this sampling library. So whatever is not in the base, for that we need to take the library.
This all the four console and the other inactive windows.
Yeah,
You are just monitoring all the four windows or
yeah,
console and other
yeah,
at the same time.
yeah.
What how this was done? Actually, I was unable to do it.
Yeah, so there is like one is that this R.
This is console.
Yeah, so in R, if here you can see in my screen, here I have used this. So this one is R, and this one is R Studio. So if you will use
Okay.
R, you will only have the console part, uh, so which is working basically here, only the console one. But if you want to have all in one, here also you can see that if I will do new script, then I can do this like I can shift it somewhere in my screen. So this one is similar to this one, and then here, but we do not have like access to everything in one place in R, so that's why I prefer R Studio. So here you can do like,
Okay.
even in the time of copying and giving someone your code, it is basically better to write it here.
Yes, ma'am,
So
that's why
yeah.
the code is available.
Yeah, all you need to do is that you need to just means for my the code is available, but if you want to do that, you can just install R Studio for that.
R Studio. Okay.
Yeah. So I think in my first class I have given. Yeah. So okay, I given. I think I'm not given, but you can just go through this RO Studio. So if I studio. So from here, you for R Studio you need to do install R. So just install, download and install R and download R Studio. So you can do your work after that in R Studio. Okay, so okay, so we will start this. So now whatever we are doing is that in that okay, so whatever we are doing, all we need to do is that uh, SRSWOR. So in that time, in sample, we are using some, we are choosing some sample, and then in that sample, we are choosing some values, and that is random or that is basically randomly, but with and without replacement. In this, we can do it separately with SRSWR and SRSWOR. So firstly we will see SRSWOR. So if I will write 10, 100, then it is this. So 000 means the values are not chosen from them, and 1 means the values are at this place. So wherever is 1, that means the value is 1. Okay, so let me do it a bit.
And
Is
just short while earlier you have said that the R is coming with the loaded R, the table, the random table it is having that or the packages.
can you repeat?
I mean that the random tables, because initially we have to prepare random tables as we have seen the lectures. He said that the random tables we have to look into the random table and then repeat while choosing the samples.
Uh, Random tables. Uh, like you can create on your own. Like
Because
if
here as you said now that we are not going to define the values. Suppose the vector x is there, so I
hmm,
need to define the contents of the vector.
hmm.
Or here it is not required.
No, here it is not required because it what it is doing is that it is saying that like here also what you can do is that when I'm saying that 1 to 10. Okay, so if it is choosing, let's say if I will run this, if it is choosing 7 7 3 to 7, then in reality I do not have sample like 1 2 3 4 5 6 up to 10. The sample is basically different, but I have given the numbers to it. If I'm running this SRSWOR 10, 100, then I am giving the number to, like, basically I'm indexing my values. So if you have, let's say, 100%, so we just index everyone by 1 to 100, and the 10 it is choosing, we are saying that okay, we will choose the people with that indexes. Means if you want to use any of these things in the real life, then we all you need to do is that index the like real data, and based on that we can do the sampling.
Okay, okay, got it.
Because just choosing some numbers doesn't make any sense in reality, na? That's why. Okay, so let's say we are doing some with some small value so that we can work with indexes. Okay, so let's say here, so it has chosen 1 2 1 1 0. So these are the indexes it has chosen, and it will always choose the different one. It will never choose a repetitive one because it is without replacement. Okay, so now we can do it again, like, or we can now save it in one, let's say, array. So S W O R 1. Let's say I have saved it by this. So it has these numbers 1 and 0. So now we can what we can do is that we can change just. SWOR1 such that SWOR1 equal to 1. So here we can see that it has 5 indexes, and if I will say 0, then it will be uh, basically 15. Okay. uh, the next is that if I will do the similar one SRW1, and if I will do SRSWR, and then 5, 20. So here we can see that it is taking 1, 1, 1, and 2. So basically this index is basically repeated, whereas the other one is not taken. So any questions?
No, no, ma'am. Please.
Okay, okay, okay. So now we have seen that we can do it like this way. So this one is basically, first one is that without replacement, next one is with replacement. Then after that, what we can do is that we can change. Now, if let's say in place of this, I am defining a vector. Let's say x is equal to letters, and then 1 to 20. Okay. So my x is basically a b c d e up to t. Now, if I'm taking that x such that, so okay, so SWOR1 here, we have is that 1 0 0 1, and then 0 0 0 1, and then this way. So if I will say that x such that this equal to 1 ADHMO. So this is, now you can see that what is happening here, that that in SRSWOR, it has chosen some 1 0 0 1 0. Let's say this 1 2 3 4 5 6 7 8 9 10. Okay. And I this one is A B C D E F G H I J. Let's say this. So the answer it is giving is that A, D, F, and H. So what it is basically that there are 4 samples which I have chosen out of 10, and then those 4 samples are basically in reality this. So these are the sample in reality, but just to choose, we are doing this indices. So this is basically 1, 2, 3, 4, 5, 6, 7, 8, 9 cents, 10. So this is basically indices. So what we are doing, that we are saying that x when s r s, sorry, whatever I have written as SWOR1 equal to 1 is basically means, so x is our real sample, and this one will give us indices. So based on these indices we will choose our real sample. So here I have written just like I have written letters. In place of that you can give some real life value, like like abcd you can take it as a person, or here also like it is working as indices. So if I will just write some array, some random array, so like we can see that the marks, so basically marks of the student in a class, and we are randomly choosing uh, because if you have a class of 10 or 20 people, there is no need to choose, we can just simply do the uh, mean or etc. But if we have a very high population, then what do we do is that we basically choose some samples, and then based on that we can do see that okay, this is the result. So if I will make a vector of this, so let's say it is 90, not 100, let's say it is out of 100, so we are doing this. Okay, so x is like 1 to 20. So if I will choose like x such that this, then it has chosen 19, 89, 45, 76, 43. So now it has done one time. So if I will repeat it again, so if I will do it again, so now SWOR1 is changed. If I will do this, so here you can see that the 87 is changed, so only 90 is remain same. So the more and more times I will use it, it will change the sample. So it will change the sample again and again. Now there is one thing. uh, let's say I'm doing some kind of simulation or anything like that, and then I do not want my sample to change it again and again, that whenever I'm using the R Studio, it is changing the sample, and it is uh, like doing a different work. Because let's say I want to run it, I have run it for the 1,000 times, and I have said that the sample mean is this much different from the population mean, so it is okay. In the next time also it will okay, but I cannot put that result anywhere. So right now, let's say if the difference is 0.37 between real sample and population mean, so then what will happen is that if I will run it again, it can be 0.38, 0.36, or 0.35. But then I cannot put the results of this at anywhere. So for that, what we can do is that we can use set dot seed. Let's say I'm writing 22, or any number you can put, like doesn't matter, 22 or 23 or whatever, like 100, 200,000. Now if I will run it. Okay, so this is the sample 78, 76, 47, 56. Let's say I'm running it again, and I have run it again. Okay, so why it is not working? Okay, okay, so here you can see that I have run it like two times. So here I just did, and I have done it like 78, 76, 47, 40, 56. And if I'm running it again, then it is 78, 76, 47, 40, and 56. So even if I'm running it again and again, then also I will get the same sample. Okay. So this was something regarding this sampling. Okay. So now you can like now once you know that, we can just play with all these things. In the second one, however, when we have SRSWR1, So SRSW.
Ma'am, SRSWOR, one is, does it have any special meaning?
Um, I have not gone through exactly that if there is any difference between SRSWOR1. We can run it, let's say.
We are using one. That does it
No,
signify?
no, I'm not using one as this. I'm just defining my vector as 1, 2, 3, 4. It is defined. I'm using only SRSWOR. Okay, so if I will define a vector as x, or I can define a vector as x1. So this is just defining it. I'm defining it like this. It has nothing to do with SRSWOR or WOR1. What I'm saying is that if there is if I'm using a function, so in the function I can give like SRSWOR and SRSWOR1. These are two functions, right? But in my definement, I can use just SWR1 or S1 or S2. Like it is a variable, so I can give any name to that. So even if I in place of this, I will define, let's say, S1 as SR SWOR 520. Then it will also be same. So S1 will also be same. So it has like I can define as S1, S or S2. So this is how I can define it. Is it clear? Okay, no. So okay, so if it is not clear, you can ask again because I cannot hear any voice right now. Okay. So the next thing is that when I was saying this SRWR1, so here right now it nothing is repeated. Okay, so now it is repeated. So we can see that this is repeated. So if I will do like the previous one where I have done this, then it will not work. Basically, why? SRWR1 equal to 1. Then what it is saying is that 111 because it is not doing 2. So what we instead of equal to 1, what we need to do is that we need to do not equal to 0. So not equal to 0 will work in SRS, basically with replacement. So without replacement also you can see that not equal to 0 will be 111 up to the indexes we want. But in SR, but in with replacement sampling we need to have this not equal to 0 to find the like what is the number which is repeated basically. So similarly, we can find that x such that, so right now here we can see that 78 is coming one time, 76 is one time, 56, and then 82 is the number which is coming two times. Okay. So in the last class, I have given one example uh, regarding this. So basically, if I have given an example that that if let's say we have 10 students uh, or 10 persons, let's say 10 people. If I have 10 people and let's say they are applying for a job, so the people are, let's say, A B C D up to this, and the jobs are basically, let's say, A, B, C. So if they are applying for the job, so simple random sampling, let's say without replacement. So in let's say in just one, we need to do the sampling without replacement in real life, because like we can choose one person maximum one time. So if I have chosen, let's say, C, D, F, then I let's say if I have chosen C, D, F, or let's say A also. Okay, then I cannot choose these people again, because it doesn't make any sense to choose people again if it is just one round. But if I'm saying that we need to choose these people and in these three companies, then there can be a repetition. So here, if it is C, D, F, A, in this sample, it can be C, E, uh, B. So C can be repeated. And in this, if I'm saying that we can have, let's say, B, D, A, so it can be repeated. So in that kind of thing in real life, you can see that if it is like one place, then repeating no, person is not, doesn't make any sense. But if I'm saying, let's say I'm taking a sample three times or four times, so basically for three places, then we can repeat, and then it will make sense that okay, C can give the interview at two place, and A can give interview at two place, B can give interview at two place D, but E and F, they can give interview at only one place. So this is, somehow you can think of some real life example, like whatever place you are related to that. Okay, so this is basically regarding this sampling and sampling package. The next we will move to the estimation of population mean. So estimation of population mean. So we will not go through the proofs etc. what we have in the class already. The basic meaning we will understand that what is the population mean and what is the population variance. So basically, that population mean is that on an average. So what is an average of this population? So this can, we can work only with numerics, and if I will give as a qualitative one, so like we see in the Amazon or Flipkart. So rather than understanding very good and very bad, so we give just number up to 0 to or 1 to 5, I think. So we give just number 1 to 5, so we can see that okay, the 1 is very bad, and then 2 is bad, and then 3 is like okay, 4 is good, and 5 is very good. So we can divide it according to ourselves, and then if the rating is greater than 4, then we see that okay, we can buy it. But what we see more is that if you go to just Amazon, and if you will see, so even if the rating is greater than 4, and let's say here the rating is rating is greater than 3.9, what we see is that how many number of people have uh, bought it, and how many number of people have rated it. So if I'm saying that this number is 80, where this number is 8K, then there is a high chance that we will buy this rather than this, because the number of people are not like buying this more. So that also matters, right? That how much is your population size, because if your population size is very small, that whatever is the uh, answer basically to that, it may or may not be correct. Okay, so the estimation of population mean, so mean is basically on an average what is its value, and the population variance is basically from the mean, how much it is varying. So as like if you have basically 1 to 100, and if you have to sample 49 and 51, and if you have to sample 101 and 100, so here the variability is very high. So even if we see that that whenever any exam happens, so let's say gate exam or J mains etc, So we can see that the where is the variability point line that matters even in the time of giving cutoff. So if the variability is very high towards the higher points, so let's say this is the like, I don't remember exactly, I think it's uh, 360 marks or whatever, let's say 1 to 360 marks. And if the population size here more and here is less, so the cutoff goes high, otherwise the cutoff goes low. So this is like in real life it uses. uh, Otherwise if it is like nearby in between, then we can see that at where the variability is low. Okay. So this is basically population mean and then population variance. So another thing is that weighted mean. So weighted mean is basically we are giving some weight to a particular point, a particular number, and some other, let's say, less weight to another number. That this matters more. So that is how also we can see that. uh, Now, the in the reality, what is that, like if we do some regarding again in a very large population, then the population mean is basically we do not know. So what we take is that we take some samples of it, and then we take the mean of its sample, and then we say that the sample mean is basically nearby equal to the population mean. Now, uh, this is called the unbiased estimator. So estimator is basically that one data whatever we have is enough to understand the second one. So this basically says that okay, one is estimating the other parameter. So we say that if I have a sample, uh, let's say y1 up to yn, and if I have a data, let's say y1 up to yn, then uh, this sample mean y bar, which is 1 by n by I equal to 1 to n, and the population mean, which is y bar, which is 1 by capital N by I equal to 1 to capital N. We say that y bar is unbiased estimator of capital Y bar. And now what it means is that if I will take expectation of Y bar, then it will be Y bar. So expectation of Y bar is basically 1 upon n summation I equal to 1 to n. So this one is Y bar. So we take that expectation of y bar is basically this 1 by n y bar, and the whole proof is given in the class already. So unbiased estimator is basically that unbiased. So basically biasness means biasedness. What is the meaning of biasedness? Anyone wants to say? What is biasness? So biased, so we have seen the example of coins, that when the coin is biased, then one will come more than another, right? So uh, in reality, that whether there is biasedness or not. So biasedness is basically, if you want to see in the mathematical way, uh, giving the more probability to one than other. So let's say if I have 1 2, just this. So I'm saying that this one, the probability is zero point 0.6 and the probability is zero point 0.4. So I mean, in the real life, if you can see that there can be some biasness, like uh, basically, like in the randomness, when we have learned, we see that uh, we, if we want to select a number between 1 to 100, then different people are biased to different numbers, that this is my lucky number, or this is my, like, let's say, birth date, or this is like summation of my birth date, so I'm going to choose this number. Or like a lot of things may go on your mind, that okay, I'm going to choose a number based on this. So this is called biasness, that I'm not unbiased, that okay, somebody has said that choose a number, I have said 76. So like if you will see it like so fast, then maybe you are not biased, but there is high chance that biasness happens. So what we can do is that for random sampling we can make the chits, and we need to fold it like in a proper way, and not use any colors, etc. So if it is all looking the same, and then we are selecting one chit, then there is a high chance that it is unbiased. So basically, uh, we are saying that it is unbiased estimator of this. So it is not doing any biasness. If the sample what we are using is biased, then the results may not be correct for the population. Because let's say I have a population, and I'm writing it, let's say 1 to 10,000. Okay, let's say I have a population up to 1 to 10,000, and on my head, like what I'm doing is that I'm choosing mostly in between 1 to 500, or let's say 500 to 1000, or some range, and I'm choosing my sample again and again from that. So whatever sample mean, whatever results it will give, it will never ever be equal to the population mean, or even nearby to the population mean, because it is very different. So this is what we have is that unbiased estimator of this y bar. Okay, so okay, so right now I'm leaving these proofs. Yeah, if you have any questions. Is there any question? Okay. No. So then next is the thing is that we will start with our next point. So next point is that so unbiased estimator we have seen already. The next is that estimation of population variance. Now why population variance is needed? So here, as we have seen that in one where is that? Okay. Okay, so what we have seen is that if I'm taking this 49 and 51, uh, and I'm taking 1 and 99. So it is basically 1 plus 99, 100 by 2, 50, 49 plus 51, 100 by 2, 50. Now the mean is same, but the variation is very high. So variance here is very high. Now if I have a sample, we want it to have a minimum variability. Why exactly? So if I have a sample which has a lot of variability, uh, then defining it, or basically understanding it anything from it will be tough. So what I want to say is basically that, let's say we have a population, and the on an average numbers, let's say, are 48, and then 52, and then 54, and then 63, uh, and then 42, and then 45, and then 43. So let's say I have this, uh, let's say I have this, is one array, and there is one more array I have, which is, uh, let's say, 17, and then 49, and then 82, and then 76, and then 44, then 33. So 1 2 3 4 5 6 7, and let's say this is 97 now. So you can't see the screen. Is it a problem to everyone else also? Well, is it a problem to everyone also that they cannot see my screen? So then I will change, like I will rejoin. Or if it is a problem to only user, then you need to join it again. Can anyone else reply? Okay, so let me just stop presenting, and then I'll present it again, and then let me know if you can see it. Okay, so can you see it again? Okay, cool. So now, what we can see here is that we have now two samples. Like this is basically one. This one is basically two. Here, you have the variability low, variability low. So basically I'm saying variability as v1. So v1 is basically less than v2. Now what I was saying is that if the variability is low, then we can really understand the real population or the sample. So understanding the real population is basically that here you can see that number are between 40 to 65. So if I'm saying that it is like in 70 or in 100, so what we can see is that I can say that the student have performed very well. Let's say if it is in 70, so student have performed very well, and some of the student, like most of the students are better than this, and the variability, if it is low. But in the second, you can see that the one person has number 17, the another person has 97. So right now I do not have I do not see the sample, I will see only the variability. So there is like m1 and v1, there is m2, and then there is v2. So let's say m1 is equal to m2. So now mean is same. So if mean is same, we cannot say that okay, both samples are good for our population, right? We need to see that the variability is also low. So if the variability is low, uh, then we can see that okay, the variability is low in the first sample. That means this sample can understand the population really well than the other one. So this is basically the need of variability. So these are not only two factors, there are a lot of factors which we will see later, that mean and then variance, and then basically what is the median, that around which the partition is happening, that 50% is population is going at this site, and then quantize or percentize, a lot of things we have. But right now we are moving to the next step, which is variability. Okay, uh, the next thing is that the unbiased estimators. So mm, the mean, as we have seen that the unbiased estimator is basically 1 by n. This y bar is unbiased estimator of capital Y bar, but here in the variance it is not 1 upon n, it is 1 upon n minus 1. So if I will say this, population variance. Uh, okay. So if I will say that population variance, uh, then so firstly we will see the sample variance. So there are two. One is okay. So first is basically 1 by n summation of yi minus y bar square, and the next one is similar. uh, Let me just write it capital, and another one I will write it with different type. So it is 1 upon n minus 1 sigma yi minus y bar square. So this is population variance, and the sample variance is basically 1 upon s square minus n1 minus n minus 1 and sigma yi minus y bar square. So you can see that capital Y and is basically small y is for sample and capital Y is for population. Okay. So now right now we can see that the only difference this sigma square and the s square is having is that mm, the difference of 1 upon n, and this is 1 upon n minus 1. So okay. So the one thing is that there are two types, and these two variances, like when we do with the sampling, these two variances we get with two methods, which is likelihood and least square. And we see that the 1 upon n minus 1 is basically the unbiased estimator and not 1 upon n. So I'm not giving any proof here. You can go through the slides for the proof. And okay. So the population variance, and then there is the variance of sample mean, and then we have the, like, for the population mean, here we have seen this sample. uh, this one is for the SRSWR, and this one is SRSWOR for both. So for both, y bar is unbiased estimator of capital Y bar. In our usually a job. Okay. Now the variance of sample mean, if we will see that, so for that we will see that what is the variance of sample mean with SRSWOR and what is with the SRSWR. So okay, so variance of sample mean under SRSWOR. Okay. So variance. So basically we are defining by V. This is Y bar, W OR. So this one is basically uh, expectation of uh, so as you can see is that here what we write is basically we write the here you can see that here I'm writing the yi which is basically units, and the y bar is uh, y bar is basically the mean. So basically the units and the mean of it is written over here. So this also, this is like y bar, so we are taking the samples, uh, sample mean y bar. So let's say I have a population, and then I have taken uh, 10 samples out of it. So 1 2 3 up to 10 samples, so each one have a mean. So it is m1, m2, and m10. So now the mean of it, this mean of it will be subtracted with this population mean. So this is basically that for the, like, let's say 10 sample or 20 samples. So this is, we have the variance of sample means. Okay, so now this one, so this one comes out to be n minus n, n, and capital S square. Uh, the variance of y bar under with replacement, it is n minus 1 upon n, n, and S square. Okay, so uh, again the proof is given already, so we are not going to that. So now what is one thing we can observe from this? What is one thing we can observe from this? This and this. Okay, so the important thing here is that you can see here it is n minus n, here it is n minus 1. So basically, I can write the variance of uh, YWR is equal to uh, N minus, uh, or we can write just WOR, let's say. WOR, I can write, let's say I'm writing it here. Okay, so I can write this as uh, n minus 1 upon n s square plus, sorry, it's not plus, it is minus n minus 1 s square upon n n, right? So it is basically, when it is with, it will be n minus 1 plus 1 and then minus n. So we can write the variability of y r and then y r as n minus 1 s square minus n minus 1 s square n. So now we know that s is a positive quantity, uh, small n is a positive quantity, s square is a positive quantity, and n if it is greater than 1. So basically that sample size is greater than 1, so which is an quite obvious thing that we're going to take sample size greater than 1. So even if not, this value is greater than or equal to 0. This means this whole value, like, because it is minus, so it is greater than 0, sorry, less than 0. So if I will say that this particular value is less than 0. And this is basically v of yr, wr. So what we are saying is that if we are subtracting something from variability of y wr, then we are getting y vywor. So what it means is that variability of this is greater than variability of this other. So because if I'm subtracting anything from here, that then after that I'm getting this, so this is truth. So what we have is that the variability in without replacement is less than the variability in with replacement. So this is one major finding, that if I'm taking a sample in which I'm doing it without replacement, then it will have the less variability than with replacement. Okay. The next thing we will see is that now if the number now the population size, now here n minus n, so let me write it again. So variability of y, sorry, this is n minus n upon n, and I'm writing it, let me write it other way, s square upon n, and then variability of y bar wr is n minus 1 upon n, s square upon n. So here you can see that this and this. Now, if the population size is increasing, then this value, these both values will reach to 1. So what I'm saying that, so let's say the population value is 1 lakh or 10 lakh, and we are taking the samples very small, let's say 10 or 1000. So in this with what we can see is that obviously we have, if n minus 1 upon n, so we have that, um, let's say if it is 1 lakh, so it is basically 1 lakh minus 1 divided by 1 lakh, so it is near about 1. Now in this we need to see that the n is also small. So basically if we are taking the samples of size 10,000, then it doesn't make any sense, we can just go through the population only. So if we are taking basically the samples of 100 or 200, then we can see that 1 lakh minus 200 divided by 1 lakh, it is almost nearby equal to 1. So that time when the population size is very high, we can see that the variability we do with replacement or without replacement, that is almost same. Okay. Now this particular thing, like here, the sample size does not matter. So in this sample size you can see that does not matter, only the population size matters. So if the population is very high, then we will not take this, and if the population size is low, then we have a problem with here. So n minus n divided by n is said to be finite population correction. So finite population correction we say, and we say that uh, the v of YWOR equal to v of YWR equal to s square upon n. But if the population is small, that's why we are saying that finite population correction. So if population is small, because otherwise it is 1 lakh or 10 lakh, we just say that population is infinite. In reality it is never infinite, but in the working process, it is infinite, we take it. So if the population size is small, we need to do this finite population correction, that means we need to multiply by this. If not, then uh, the both type of samples will have this same correction, sorry, same variation. Okay. Okay. Okay, so the next, we gone through this already. So let me see if any point is remained. Otherwise, we will just move through uh, the next one. Okay. So the next is that the estimation of population variance. So we have seen what is population variance, what is the variance of sample mean under different like SRSWR, SRSWOR. The next is that estimation of population variance. Okay. So next we will see what is the estimation of population variance. So the variance of uh, basically, let me see the case one, which is SRSWOR. So the time when we have SRSWOR, the estimation of S square. So E of S square is basically uh, S square, and if we see this SRSWR, then expectation of S square is sigma square. So these two we get as S square and sigma square. So again, the proof is already in the class. So it is very two-line proof. So all you need to do is that estimation of S square, we need to just put the values for that. Mm, okay. So okay. So the next is that what is important in SRSWR, we have this S square, and in SRSWR we have this sigma square. Uh, so here for SRSWOR, uh, small s square. Let me write it small s. Small s square is unbiased for capital S square, and in SRSWR, small s square is unbiased estimator for sigma square. So these two have basically unbiased estimator. So the simple meaning of unbiased, basically if expectation of one estimator is equal to uh, the population variance or mean, etc., then so in the previous one, for the mean, we have seen that just the mean is estimator, unbiased estimator for the population mean, but here the unbiased estimator are different. So for WOR, it is unbiased estimator of capital S square, and for the SRSWR, so basically with replacement, we have this different estimator. Okay. Then Now, the next thing we have is that standard error. So, standard error of y bar. So, a standard error of y bar, we can define it as a plus minus variance gap of y. Uh, we can divide it like this, but it is like a square root. So if we have like theta cap is unbiased estimator of theta, let's say, then root cap, it is not necessary. This one is not necessary. So that, because when this happens basically, so when this happens, you may remember that in the very basic thing, let's say, when we have expectation of c, where c is constant, it is c. When we have expectation of root c, it is root c. So basically it happens when it is constant, but as soon as I'm saying that it is not c but it is x, so this is not true. Like if I'm saying that expectation is x, then this is not necessarily true, because then there is no need to solve the function or like work again, because what will happen, variance is basically expectation of x square minus expectation of x whole square, right? So if I'm saying that expectation of x is x and expectation of x square is x square, so what will happen? It will be basically x square minus x square, which will be 0. So that means if this is the case, variance of x will always be 0. It will never have any value, right? But this is not truth. This is false. So expectation of x is x, then it is not necessarily true that expectation of x square is also x square. It may happen in very rare case. For constant values it is true, but for the variable it is not true. So basically if we have expectation of x, then expectation of x square cannot be x square. So similarly the expectation of root x is also not equal to root x. So what I want to what I'm trying to say from here is that the uh, the estimator we have, which is plus under root variance of y, this is a standard error, we can see that, but it is not unbiased estimator for the real population. Okay. So this also means that the estimators what we have for sigma square and the sigma, so basically sigma square for variance and sigma is for deviation, so these are also different. Okay. So this one does not have the property similar as the variance of y. So this is basically regarding the today's class what we have learned. Uh, so now we will do some question answers based on that. Uh, so these are some basic questions which we have learned, just like whatever we have learned. So it is just a basic repetition of that. Okay. So first question is that which one of the following can be the valid outcome of executing SRS WOR 48? So SRSWOR is basically draw 4 units without replacement from 8. So we can see that in the first one, there are 4 units. So this one is the correct answer. In the second one, there are 5 units. So basically 1, 2, 3, 4, 5. So this is not correct. This is not correct because all 0. This is also not correct because there is only 2 ones. So this is that we need to see how many ones are there. Okay. The next one is that uh, you can say what is the answer. Which balls have been selected here? Okay. So basically, we have what we have done is that we have taken 1 2 up to 8 balls, and then we have given them numbers 1 2. So
Madam, excuse me.
yeah,
Madam, excuse me, madam.
yeah, say.
Hello?
Yeah,
Hello?
say. Yeah, hello.
Hello, madam?
Yeah, say. Like I'm listening.
Hello? I'm audible, madam?
Yes, you are audible. Okay, let me do this.
Hello? I'm audible, madam?
Yes, you are audible, but am I audible to you? Is it a problem?
Ma'am, your voice is not clear, ma'am. That's why.
Okay. Is it still not clear?
No, it's okay, ma'am.
Okay, so maybe because of camera, sometimes maybe the net is slow. Okay.
Due to, I think, due to net issues.
Okay.
Okay,
So
ma'am, continue.
okay. Okay, so in this one, so we have basically indexed the ball 1 2 up to 8. So the number of balls we are selecting. So basically in the one it is selected. So of the one it is 3. So it will be 1 3 5 7. So these are very basics. Okay. The next one is that uh,
1357.
what are you saying anything?
Please continue, ma'am. Please continue.
Okay, okay. So in a sample of 10 balls, so all you need to do is that questions are simple, but then we need to see that what is the question exactly. So here we have that which are not selected. So in the not selected, we need to see where are zero presents. So we can see that it is present in the one, fourth, and then six, and then eighth and nine. So this one will be the answer.
Yeah, 14689.
Okay, so in this, it is basically we are doing SRSWR 57 returns the vector 0 2 1 0 1 0 1. So we have selected 5 balls. So which ball is selected more than once?
Ball 2.
So ball 2. Basically, this one is first, this one is second, third, fourth, five, six, seven. So in the second place, it is selected. So ball 2 is selected more than once. Okay.
Ball 2.
Yeah. So in the next question, we have a data vector, which one can count that SRSWR samples, uh, which our command will extract only non-zero counts. Okay, so we need only non-zero counts, sampled counts. So
More
this
than
one,
zero C, I think.
so no, if we will say greater than or equal to, so zero will also come in that. So C is not correct. Uh, so we have non-zero means
Will also
zero
come.
cannot
More
come.
than zero.
Okay,
So only the last one then comes forward.
okay. So okay, so in SRSWR, what we have seen here is that we take not equal to 0. So if it is not equal to 0, so whatever will be 0 can come. So this one is correct answer and this one is correct answer when we are doing about sample. So only now non-zero counts will be like in general only non-zero counts will be covered only by x not equal to 0, uh, right? Because
D
if
is
there
correct.
is
Right, right.
right, then if
Yeah.
there is anything like less than 0 it will also count, but in the sample we do not have less than 0, so there is nothing like minus 1 sample. So here we can also take x greater than 0, so B and D both are correct answer here. Okay. The next is that which statistic is always an unbiased estimator of population mean when drawn from a simple random sample. So simple random sampling basically it can be with replacement, it can be without replacement. So what is the statistic which is unbiased estimator? Is it sample median, sample mean, sample mode, or sample range? So we have just gone through all of this, that for the population mean, which one is the unbiased estimator. Okay. So here if we will have a look into that, so sample mean, if we have sample mean and population mean like this, so we say that the expectation of y bar is basically 1 upon all the samples. uh, So it will be divided by the population and then summation of all yi. So this is capital Y bar. So basically small y bar is the estimator, unbiased estimator of capital Y bar. So this says that the sample mean is one thing which is unbiased estimator of population mean. So sample mean will be the answer. The median, mode, and range are not the unbiased estimator of population mean. Like not always, but if you will see that the normal distribution, in normal distribution like mean, median, mode, all are equal. So in that case, it is like sample mode also you can take whatever is easy for you. If you think that calculating the mode is easy, then it is unbiased estimator of population mean. But in always case it is gonna happen every time, then it is sample mean. Okay, the next question is that let am1 be the sample mean for srswor sample, and which one of the following statement is true. So we have seen just in the previous question that it is not biased, it is unbiased estimator of population mean. Okay. The similar question we have here with SRSWR. So it is either SRSWR as SRSWOR does not matter with or without replacement. The sample mean will always be the unbiased estimator of the population mean. So this is basically the theory which is gonna be true always. Okay. The next question is that we have just seen in the last. So, what is the finite population correct effect? Sorry, finite population correction factor used to adjust the variance of sample mean in SRSWOR. Okay, you can take some time and you can see that what can be the answer of it. Okay, so let me just go through the slides we have seen already. So here we have seen that population variance, sample variance, and here we have seen that this one is this one is variance of without replacement, with replacement. So s square upon n, s square upon n. So this is finite population correction. So n minus n upon n is finite population correction. So n minus n upon n will be the correct answer. The next question is that we have the observation y1, y2 up to yn observations from SRSWOR. Which of the following is an unbiased estimator of population variance? So, as I have said in the very starting, that for the population mean, the unbiased estimator is y bar. Uh, here. But for the sample variance, so for the sample variance, basically this 1 upon n minus 1, this one is the unbiased estimator. So here, here. Here you can see that estimation of population variance. So for SRSWOR, the estimation of S square is equal to capital S square. So this is basically 1 upon n minus 1. So it is not 1 upon n, it is 1 upon n minus 1 sigma yi minus y bar whole square. The next question is that two independent samples are drawn from SRSWOR. If their sample mean is averaged, is the resulting estimator unbiased for the population mean? Okay, so let me clarify this question. So basically, we have two samples we are choosing from SRSWOR. So I have basically two samples. So s- means basically like a sample consisting of some units. So sample size can be 10, can be 20, etc. So let's say it is sample S1, it is sample S2. It is saying that if I will take average of sample means are averaged, so average of sample means, then is the resulting estimator unbiased for population mean or not? If I have sample, let's say S1, okay, So let's say I have one sample and the mean is basically M1. Here the mean is basically M2. So in the unbiased estimator, what we have learned is that as if I will say E of M1, and let's say uh, the population mean is capital M, right? So we have these values. So if I so what we know is that from the estimator theory, we know that the mean sample mean is unbiased estimator of population mean, which means that E of M1 will equal to 1, sorry, M. So that means M1 is unbiased estimator of capital M. So E of M1 is M. Similarly, E of M2 will also be M. Now, what I am saying is that I have a sample and I'm taking the average of it. Okay, so let me just remove this one. Okay. So now I'm taking M3 mean, which is M1 plus M2 by 2. Now the question is that is it unbiased estimator or not? Okay. So expectation of M1 plus M2 by 2. Expectation of M3 is basically expectation of M1 plus M2 by 2. Now with the property of expectation, because it does not hold every time, so with the property of expectation, what is the property of expectation? So basically the expectation have this nice property that E of x plus y is equal to Ex plus Ey. Also, the expectation of Cx is C expectation of x, where C is constant. Okay, so I can write this as 1 upon 2 because it is like C expectation of M1 plus expectation of M2, because expectation of x plus y is again expectation of x plus y plus expectation of y. So it will be 1 upon 2. The expectation of M1 is M, expectation of M2 is M. So it is M plus M, it is 2M upon M, sorry, upon 2. So it will be M. So what we have is that expectation of M3 equal to M. So when does this happen? It says that M3 is unbiased estimator of M. So what we have is that uh, if we take the average of it, is the resulting estimator unbiased for the population mean? So it is yes, that average of unbiased estimator is unbiased. Okay. Now the last question we have, I think, yeah, the last question we have is that sampling error refers to. So I cannot have any questions. Okay, so what does sampling error refers to? So error made during the data entry, or error the natural variation that is occurring, or the mistakes in the measurement instrument or bias introduced by the non-random selection. Okay, so sampling error happens why? So, uh, the time when we are saying that sampling error or standard error or whatever we have, the sampling error, basically we have the sampling error, sampling variance, etc. We have because uh, not because the errors are made during the data entry, because if it is made during the data entry, then we need to change our samples, right? So if let's say my population, uh, okay, so let's say if my population is uh, regarding uh, the number of marks, basically I in a class of students. So if I have done, let's say there's a class of 50 students and we have worked with that, I think, in our BSc, etc. So if it is, let's say, 30, 35, 46, etc., and then 52, let's say, let me remove this. So it is, let's say, 50 and then 43. So if I'm saying that no, there is no student which has got the full marks, actually the in place of 50, it was actually 48. So there was some mistake, something I have added two times. So now the population or whatever samples we have taken, so if the data entry is wrong, we need to do all the calculation again. So it is not the sampling error, it is the error, like which we cannot ignore. So sampling error is basically something which, sampling error is basically which we try to like reduce. Okay, so this is not true. The mistakes in is measurement, not true, and biasness we will see. The next one will true, the natural variation that occur by selecting a sample rather than measuring the entire population. So this is basically the sampling error, because if I have the entire population, if I will go through that, so work is very high. So if I will go through the entire population, it will give me the exact value, but then working on that will be too much and it may cost too much. So that's why we take samples, and that is why there is some error with respect to the population mean. The last one is that bias introduced because of non-random sample. So if we are taking non-random selection, then it is a different case. So that will have the biasness obviously, but that is not sampling error. That means we are choosing to have that kind of error or whatever it takes, because we are not choosing our sample randomly, or we are choosing on a specific reason, then it will not contribute to the sampling error. So this is one of the reason. Okay, so this one is all regarding the today's class. So if anyone have any questions, they can ask. Okay, so in just brief, I'm gonna just repeat it in 5 minutes. So, firstly, we have gone through the sampling package, and we have seen that firstly we need the library for that. Also, if we introduce set.seed and then we use any number inside it, doesn't matter really. And if we do that, then the sample, whatever comes one time, it will come again and again. Otherwise, if we want to take different samples, then we will not use it. So we have taken SRSWOR for with replacement, and WR function for sorry, without replacement. Second one with WR for with replacement, and this one is to take the data entry, that whether it the indices has come or not. After that, we have seen the estimation of population mean, that how do we estimate it. The next we have seen is that what is the population, what is the unbiased estimator of population mean. After that, we have gone through the estimation of population variance, and in the population variance, uh, we have seen that for the population mean it is same for with and without replacement. However, for the population variance, the cases are different, and the population variance, we can see that it is less. Sorry, the variance, when we have under the SRSWOR and we have SRSWR, we can see that the variance is high in WR. In with replacement, the variance is high in comparison to without replacement. After that, we have seen that if the population size is enough, then it really doesn't matter that which one we are taking, whether it is without replacement or with replacement. Then time its variance will be capital S square by n. After that, we have seen the estimation of population variance is different. So, for S square, the unbiased estimator is small s square in the time of without replacement. However, for with replacement, it is unbiased estimator for sigma square, not for S square. And then we have seen that a standard error, what is a standard error, and how it is not an unbiased estimator for the standard error of real population. Okay, so this is regarding today's class. Again, if anyone have any question, they can ask, or otherwise I will just end the class in this. Okay, so right now, if you do not have any question, you can write in the discussion form, and uh, in the meantime, like I can go through that, and I can see we can resolve those issues there. Okay, then thank you for joining this class.
Thank you, madam.